guys, today we're going to talk about seasons. So I want to start off with the question, why do we have seasons? And this is a question that you're going to have to be able to answer. And the answer is interesting because a lot of people don't really know. A lot of people think something that causes the seasons, why winter is different than summer, has something to do with the distance from the sun. So I'm going to play a quick video clip about that right here.
Why do we get the seasons?
The seasons? Because of the atmosphere?
To be honest with you, that's a very easy question to answer now. We really don't get seasons anymore because of global warming. I think there was a time when I was a child where we definitely had 4 seasons, but I think now we get summer, 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 and a little bit of winter in Australia.
Is it to do with the Earth's turning and the equator? 4 seasons?
You mean like summer and winter and autumn and spring?
Doesn't it come from where we are around the sun? And at that stage, that's the season that we're in.
I think the position of the Earth, depending on the sun, it's like if the Earth is standing other positions to the Earth, and there's winter, summer, and in the between there's autumn and spring.
Because the Earth rotates on an axis, right? And I think, so it goes around on an axis.
Well, obviously the Earth isn't like spinning like that, it's sort of like on an angle. Because of the axis of the Earth rotating, around its axis.
Yeah, what does the axis do?
It seems to be further and closer to the sun.
Sometimes the sun is actually glancing the surface of the Earth in certain regions, and other times it's square on, like perpendicular.
Well, basically, the sun's rays are more oblique at certain times of the year than at others.
I think it's because of how the sun rays are like hitting. When they hit at an angle, it doesn't get that hot.
Okay, so seasons are a result of really 2 things. Number 1, the tilt of Earth on its axis. And we already learned that the Earth is tilted on its axis at an angle of 23.5 degrees. And it also revolves around the sun, so it makes a path around the sun. So the orbit has something to do with it, as well as the tilt. Now, it is not a result of the distance from the sun. And that is often misunderstood. Now, there's something called the vertical ray, which I'm going to show you in a second. That has something to do with the angle of the sun striking the ground. And that's what we're going to work on for a lab dealing with this topic as well. But again, the big factors here are the tilt of the Earth, as well as the path or the revolution of the Earth around the sun. Okay, so this kind of shows that in a simple diagram. We have 4 different seasons here. We have the summer solstice, June 21st. The autumnal equinox, September 22nd. December 21st or 22nd is the winter solstice. And then the vernal equinox over here on the far side. Notice how this is the orbit. It's called an ellipse. It is a slightly elliptical orbit, but the difference between here and here is only about 4 million miles. So it's not a huge difference, like 3% different. But it's interesting, we're actually farther away from the sun in winter than we are, we're farther away in the summer than we are in the winter in the northern hemisphere. And remember, while we're having our winter, the southern hemisphere is having their summer. So it can't have anything to do with our distance from the sun. It has everything to do with our tilt. So this diagram kind of shows that. So in summer, in our summer, northern hemisphere summer, June 21st is the first day of that, the Earth's North Pole is tilted toward the sun. And therefore, as you can see here, we receive more direct rays of the sun, a more vertical ray of the sun shining on the Earth. We have a longer daytime period as well. In fact, the North Pole is 24 hours in the sun. For us in New York, it's around a 15-hour day, which you guys did the other day. So this tilt of the northern hemisphere toward the sun means that's got to be summer. Notice down here in the southern hemisphere, it's got to be winter because their south pole is tilted away from the sun. Now flip 6 months later and look, the North Pole is now tilted away from the sun and the South Pole is tilted towards it. So that would be southern hemisphere summer. and northern hemisphere is winter. Notice how long our day is. We have a lot of time in the dark here and less time in the light. Also, this angle with the horizon here, this would be the horizon right along that line. This angle coming in is really shallow, so we don't have direct light as much. Okay, the sun is a lot lower in the sky. There's the equinoxes, spring and fall, and notice how everybody gets 12 hours of daylight. That's why we're kind of in between the seasons. It's not exactly really hot and it's not exactly really cold. It's like Goldilocks in between. Okay, so that's the reason for the season. It has everything to do with tilt, and you can see obviously the tilt stays the same. We just make a path around the sun. That's kind of shown in this diagram. We're always tilted towards Polaris, and the sun stays still and we go around it, and therefore sometimes we're tilted toward or sometimes we're tilted away. Okay, and this kind of shows the exact same thing, so I don't need to spend a lot of time on that diagram. Now here's another really cool thing about the revolution around the sun that has something to do with our stars that we see in the night sky. So as we make this big long path around the sun, 1 year, one revolution around the sun, not only do we have different seasons because of our tilt, but also we see different constellations in the night sky. So in some times of the year, like in winter and around now in fall, we can see this constellation over here because our nighttime side is on that side. So we are looking at night at Orion, so we can see Orion in the winter. But if we travel around the path over to the other side, now we're over here, in order to look at Orion, we'd have to look this way at Orion over there, right? Because it's over there in the sky, and we wouldn't be able to see it because the sun is shining. It would be daytime. So we would have to look at these other constellations on this side, like Scorpius. That's a constellation that we can only see during the summertime. So an interesting idea is that we can only see certain constellations at certain times of the year based upon our path around the sun. So here's our great picture of the Earth inside of the celestial sphere, something that we've been talking about for the last couple of weeks. You can see the Earth is tilted on its axis in this picture, and you can see the constellations and the stars around us in the night sky are embedded on this celestial sphere. Even the sun is on the celestial sphere, and it takes this yellow path around us and this stationary object in the middle of the celestial sphere. Remember, realistically, the Earth is moving, not the sun going around us, okay? And therefore, this is a little bit misleading in some ways. This yellow line is called the ecliptic, and you can kind of see it here in this red line. The red line is the ecliptic, okay? Now this kind of leads into the idea of what is the ecliptic? What's the ecliptic all about? So I want to show you an animation of the ecliptic that goes right along with this diagram, and I'll show that right here. All right, guys, I really like this animation, which kind of shows how the celestial sphere and the ecliptic are connected to each other. So you can kind of see this, I'll pause it, this blue line represents the orbit of the Earth around the sun. And now coming into view, you can see this kind of grid coming into view. And now we're going to put the whole entire thing inside of the celestial sphere. Okay, so you can see, we're going to zoom out a little bit, and the celestial sphere is now visible. And so you can kind of see how the celestial sphere and the sun fit together here. And what we're going to see is this path that the Earth takes around the sun is going to be displayed onto here. It's going to be a nice flat line that'll be displayed onto our celestial sphere here in a second. So let's just let that rotate, and you can watch and observe, see what's happening. So watch the plane of the Earth's orbit, that pinkish purplish stuff that's going to come in. That's the plane of the Earth's orbit, and that's called the ecliptic. So the ecliptic is the line that represents the orbit of the Earth around the sun. For us as observers on Earth, and we're imagining the stationary model, this basically represents the path that the sun takes around the celestial sphere. So that's called the ecliptic path. And now you can see that displayed. So that nice pink line on there is the celestial sphere. And you can kind of see how it's tilted relative to this. So it's a 23.5 degree tilt. And that's the ecliptic path there. Okay, so I want to show you how this diagram is associated with this diagram. So you can kind of see there is the path of the ecliptic, the yellow line there, And the way the sun goes across the sky can be displayed by cutting this in half into two different sides. So if you cut it in half, you'll get two different sides like this. And here's our red line to represent the path of the sun throughout the entire year. We start here on the right-hand side. That's 0 hours of right ascension, which basically means that's the first day of spring. And then we work our way up the ecliptic, and the sun gets to right here, and that's the first day of summer. Notice how it's really high in the northern hemisphere. So it's at a more direct angle in the northern hemisphere. So that's our first day of summer. Then we come back down again, back to this point on the equator. That's the autumnal equinox, first day of fall. And then we go back down into the southern hemisphere. This is our first day of winter here in the north, first day of summer in the southern hemisphere. And then back up again to start all over again at spring here at the vernal equinox. So that's kind of related to this whole idea of what's called the zodiac. And the zodiac is essentially just a bunch of constellations that are along this path, along this red line. And those constellations were observed by a lot of astronomers back in ancient Greece. And so I'm going to show you guys a video quickly about the zodiac right here.
13 constellations that have been studied and tracked since ancient times. The constellations in the zodiac are all highly visible from Earth during different months of the year, starting with Sagittarius in January and ending with Ophiuchus. And last time, we saw how these constellations form a sort of belt-like shape around the Earth. Well, this time, we're going to see what the sun's up to while the constellations take turns popping up in our night sky. Okay, so there's Earth in the middle of space. Looking good, home planet. And here are the zodiac constellations that surround Earth. But we've got to make room for another major player in space. You remember the sun, of course. Earth, scooch over. Sun, head to center stage. You're on. Okay, you already know that Earth rotates on its axis, making a complete turn in one day. While it's rotating, it also revolves around the sun, making one full trip around the star every year. This movement of the Earth also makes it seem as if the sun is moving through the stars over the course of the year. This is because during any given month, the sun sits between the Earth and a different zodiac constellation. But we know the sun's not really moving. It's the Earth's movement that makes it seem that way, and astronomers have come up with a nifty way to track the sun's apparent path through space. They draw an imaginary line from the Earth through the sun and toward the stars beyond it. As the Earth moves, so does this line with it, while the sun stays steady in the middle. As Earth follows its orbit around the sun, this imaginary line spins, pointing to different stars throughout a complete trip around the sun, forming an imaginary circle. Astronomers call this imaginary line that the zodiac sits on and that tracks the sun's apparent path through space the ecliptic. Eventually, over a year, the Earth will return to Sagittarius, where it started, and the cycle, or pattern, will start all over again.
Okay, so last thoughts based upon that video. You obviously saw in there that these constellations around the ecliptic are called the zodiac. We start with Sagittarius in January, and that would be when the Earth is over here actually in the orbit. We can look and line it up with the sun and Sagittarius would be lined up in a straight line. Okay, and Earth would be over here. As the Earth moves around, that will change. And in June, we'd be looking at Taurus would be lined up with the sun. Okay, so that's why the zodiac constellation for that time of the year is actually Taurus. So just so you're aware, it's when it's lined up with the sun and pointing on that side. So we make this entire revolutionary path in 1 year, seeing all these zodiac signs throughout the year. And remember, all of those zodiac signs are falling along this nice red ecliptic line throughout the entire year. Okay, so big takeaway is we see different constellations throughout the entire year because of our revolutionary path around the sun, and the ones that fall along the ecliptic are called the zodiac. And the other takeaway is the idea that seasons are caused by the tilt of the Earth on its axis, and that tilt remaining constant, pointing at Polaris the whole time, and different parts of the Earth will receive the vertical ray, meaning they'll receive more direct sunlight. Okay, so that's the big takeaway, and we're going to do a lab related to this as well. So if you have any questions, just let me know, and hope that all makes sense to you.